Okay, we're going to continue our discussion of chiral molecules, and here we're specifically going to talk about how to designate them as being either the enantiomer as being either the R or S configuration. So we need some way when we're talking about a compound to distinguish it from its enantiomer. And in the IUPAC system, what we use is what's called the Kahn-Ingold prelog system. And in this system, one of the two enantiomers will be designated as R, and the other will be designated as S. And so I'll give a quick summary here, and then we'll go through this in more detail. So the first thing we do is we prioritize all groups connected to the chiral center by their atomic number. So the highest atomic number gets assigned as priority 1, the second highest atomic number gets priority 2, and then 3 and 4. If necessary, we need to rotate the molecule so that the fourth priority group is in the back using the dash wedge notation. And then for the other three substituents that we've assigned priority 1, 2, and 3, if those go in clockwise order, it's going to be the R configuration. And if that goes in a counterclockwise order, it's going to be the S configuration. So here's an example. We want to first assign all groups a priority. And so the atom with the highest priority will be assigned 1. Right? And so here's my chiral center. And so I've got a chlorine, an oxygen, a hydrogen, and a carbon. Right? So chlorine has the highest atomic number, so it gets assigned a priority of 1. Right? Then oxygen comes in next, followed by carbon and hydrogen. And so my priority 4 group is already in the back, right? It's on the dash. If it hadn't been, we'd have to worry about rotating it, and I'll talk about that more in more detail later. The first couple examples we're going to do are going to be such that we don't need to do this rotation, right? So I can essentially skip step 2 because the priority 4 group is already in the back, and then I just look at the 1, 2, and 3, right? And so this is going from 1 to 2 to 3. It's going in a clockwise fashion, and so this is going to be the R enantiomer. And one way to remember that, the difference between R and S, right, if I start at, the top of the clock, if I start at 12 o'clock, right, clockwise is going to the right, so that's my R enantiomer. If I look at this molecule over here, right, same groups, but now when I assign the priorities, right, they're the same, but things moved around, right? So I've got 1, 2, 3, right? So 4 is still in the back, and so now I can look at this 1, 2, 3, right? Now because we're going 1 to 2 to 3, we're going counterclockwise. This is the S enantiomer. All right? Now it's not always so easy to assign the priorities. Sometimes there are ties. And so what we do is if there's a tie, as in this case, right, so it's pretty easy, right, I've got oxygen, carbon, carbon, hydrogen. So I know the oxygen is going to get priority 1, the hydrogen is going to get priority 4, but for the 2 carbons, right, which one gets 2 and which one gets 3? And so what we want to do is, starting with the ones that are a tie, we'll make a list of the other 3 atoms that they're connected to, going from highest molecular weight to highest atomic number to lowest atomic number. And so this carbon is attached to one other carbon and then 2 hydrogens that obviously aren't shown, right? So he's CHH. When I do the same thing for this one, right, it's also attached to 1 carbon and 2 hydrogens. So we're still tied. And so what we do is we go out systematically in sort of layers. And so next I'm going to go to this carbon and this carbon. And so the things that this carbon is attached to, it's attached to 2 carbons and a hydrogen. In addition to, right, I'm ignoring the one that it came from. Right, it's attached to a carbon, and then a hydrogen we're not showing. So it's CCH. Right, and then the other things that this one is attached to are a carbon and 2 hydrogens. So it's CHH. Right, so now when I look, right, the first ones are a tie, but then here's my tiebreaker. And so carbon has a higher atomic number than hydrogen, so this was the first time we had a difference, and so this gets the higher priority, or it gets to be 2. When I say higher priority, I guess I really mean lower, right? So that gets to be 2, and then that one is going to be 3. The hydrogen still is 4, and the oxygen still is 1. So I don't have to rotate, so I can assign, right? I'm going 1, 2, 3. It's counterclockwise, and so this is my S enantiomer. Okay, one more example where we still don't have to rotate, but where we're going to need to look at tiebreakers as far as assigning priority. And in this example, I realize that this is also a chiral center, but we're just going to focus on this one for this specific example. And so when I go to assign my priorities, again, the fluorine has the high, right? I've got carbon, carbon, fluorine, hydrogen, right? So I've got priority 1 and 4. Now, when I go to the carbons that are tied, I've got this carbon and this carbon. For this one, when I go to what it's attached to, it's pretty easy, right? It's got an O, and then a carbon, and then an H that's not being shown, right? So he's got OCH. When I look at this carbon, we count the double bonds as 2 of that type of atom. If it had been a triple bond, we would have counted as 3. So I have a double bond to an oxygen, and then a carbon, and so his list is going to be OOC. And so then when I'm looking at, for the tiebreakers, right, the O's tie, and then here's my tiebreaker. I've got carbon versus oxygen. So oxygen has a higher atomic number, so that gets priority 2, that gets priority 3, and now for this chiral center, 1, 2, 3, so this chiral center is clockwise, so that chiral center is going to be R. Okay, so let's talk about what we have to do when we do need to rotate the molecule. This can be hard, and the book recommends looking at models, but that's not always available to us. And so we have another really helpful tool. It turns out that if I switch any 2 of the groups of a chiral molecule, I will get its enantiomer. And in this case, they've switched these 2, but we could have picked any 2. If I switch any 2, if I'd started with the S, right, and it's going 1, 2, 3, this is going to be the R, because I just switched 2 of the groups. So what's super helpful about that, if I'm trying to assign the R or S configuration of a given molecule, if I switch 2 groups, right, so I put the 4 in the back as I need to have, right, but now I've changed to the enantiomer. If I switch another set of 2 groups, right, now I'm back to the same configuration that I started with. And so my 4 is in the back, and so I can assign the configuration, and I'm going 1, 2, 3, I'm going clockwise, so I know that that's R. To get to that, I came from here, and to do that, I switched, right, these 2, so that means this must be S. To get to this one, I switched these 2, and so that means that must be R. So if my 4th group isn't along the dash, all I've got to do is make 2 substitutions and and then make sure that the 4 is in the back after those 2 substitutions, and then that will be able to tell me what the configuration of my original compound was. All right, so just a quick summary here. In order to assign the configuration of a chiral molecule, or of a chiral center, I guess I should say, we assign a priority to each atom on the chiral center based on atomic number. The highest atomic number gets a priority of 1, the next highest gets a 2, then a 3, and then a 4. If there's a tie when we're assigning priorities, we sort of move away in layers, right? We make a list of each of the other atoms that tie was connected to, and we keep going until we get a difference. And then remember that double bonds count as 2 single bonds, triple bonds count as 3 of those single bonds. Then, if necessary, we need to rotate the molecule so that the group that we assigned a priority for is in the back, so that it's on the dash. Remember that 1 switch gives us the enantiomer, 2 switches gives us back the original configuration. Finally, once we have the priority group 4 in the back, if the 1, 2, 3 sequence is clockwise, it's our R configuration. If the 1, 2, 3 sequence is counterclockwise, then we have the S. All right, so for each chiral center in each of these examples, we want to assign it as being R or S. In this case, I think we only have the one chiral center. And what they've done here, and this is typical of what we'll often see in the examples, is right, they haven't showed us they're not showing us the hydrogen, right? But if these two are in the plane and the NH2 group is going back, then that means that, right, the hydrogen has got to be on the wedge. And so when we go to assign priorities, I've got carbon, carbon, hydrogen, nitrogen. Right, so nitrogen has the highest atomic number, so I know he's going to be 1. Hydrogen has the lowest, I know he's going to be 4. Right, and then I've got to decide between these two carbons. Right, so when I look at this carbon, it's attached to a carbon and 2 hydrogens. So it's going to be CHH. This carbon is attached to 2 carbons and a hydrogen, so it's CCH. Right, so here's my tiebreaker. So this one gets priority 2. This one gets priority 3. But now here's where we're going to have to rotate, because in this example, right, my priority 4 is not in the back. Right, now rather than redrawing the whole dang molecule, which would be kind of a pain in the butt, what we can do is just, right, here's what we're starting with. I've got 2, 3, 4, 1. So if I switch 4 and 1 and 2 and 3, then I'll have done 2 switches, and then that will allow me to assign the configuration of this molecule. So what we're going to end up with is switch the 2 and the 3, switch the 1 and the 4, and so now my 1, 2, 3 is counterclockwise, so I know that both in this form and in the original, that chiral center is S. Now, I guess one thing I should say, when I do this, drawing these out is great, but as you do more and more of these, you may be able to find shortcuts. And in fact, when I do this, I don't even redraw it, right? I go through and I assign my priorities just like we did here, and then doing 2 switches in my head for me is kind of hard. But I can do 1 switch, and then I know whatever I get, the actual answer is going to be the opposite. Right, so this is confusing. You can just fast forward to the next slide. But if I was looking at this, what I would do is I would say, okay, I'm going to switch these 2. And so I know this is really going to be 1. And so I'd go 1, 2, 3. So that's clockwise, and it's R, but I only did 1 switch, and so I know it's S. So I can do 1 switch in my head, and then I just know whatever I get, my answer is going to be the opposite. If you don't like that, just ignore what I just said, right? You can always redraw these guys. Okay, here's one more example. So I think in this case, I have a chiral center here, right? These carbons are not the same. I've got a carbon with a bromine and a chlorine. This is not a chiral center because I've got 2 methyls, right? But I think this is, because this carbon is not the same as this carbon. I've got a bromine and I've got a hydrogen. So let's start with this guy on the left. So I've got a chlorine, a bromine, and 2 carbons. So I think it's easy to say, right, bromine is going to be 1, chlorine is going to be 2, but now I've got to look at my carbons, right? So when I look at this guy, in addition to this one, he's got a C and 2 H's. So he's CHH. When I look at this one, he's attached to a chlorine, and then the double bond is 2 carbons. So that carbon is going to be ClCC. So my tiebreaker is with the first one. So that's going to get priority 3. That's going to get priority 4. All right, let me move this up a little bit. And so what we're looking at is we have 2, 1, 3, 4. So what I'm going to do is I'm going to switch 1 and 4 and 2 and 3. And so what I'm going to end up with then So I switch the 1 and the 4. So the 4 goes to the back, the 1 goes in front. I switch the 3 and the 2. And so now I'm going 1, 2, 3. I'm going clockwise. So this chiral center is R. All right, and then when I look at this guy, I've got a bromine, carbon, carbon, hydrogen. So they're not showing the hydrogen, but I know, right, because the bromine's going back, the hydrogen's got to be coming out towards me. And I know bromine's going to be 1, hydrogen's going to be 4. So then now I've got to break the tie between these two carbons. And so this carbon is going to be CHH. This carbon is going to be ClCC. So again, my chlorine beats my carbon. So that's going to be 2. That's going to be 3. So I've got to rotate it again. And I've got 3, 2. I've got the hydrogen coming out at me. I'm sorry, I've got the 4 coming out at me. I've got the 1 going in the back. So I'll switch 1 and 4, 2 and 3. So I've got 2, 3. 1's coming out at me. 4's going back. And again, 1, 2, 3, we're going clockwise. So this chiral center is also R. So this doesn't have to be the case, but both of my chiral centers in this case happen to be R. Okay, and then one final note on nomenclature. When you assign the configuration to your molecule and you name it, if there's just one chiral center, then you would just put that designation out in front. And I know we haven't named alcohols to this point, but whatever the name of your molecule is, if there's just one chiral center, we would put the RS designation out in front. In this molecule, there are 2 chiral centers. So if we just put, in this, I'm not going to go through it, but this happens to be R, this happens to be S. If we just put R and S out in front, we wouldn't know which one was which. And so if I have more than one chiral center, we've got to specify the location. So if I was doing naming of this compound, right, I'd have 1, 2, 3, 4, 5. And so the number tells me the position that I'm talking about. So I'm saying, okay, position 2 is chiral, it's R. Position 3 is also chiral, and it's S.